questions on the homework?
Can you work with the site?
The radioactive substance decays exponentially. M0 is the initial mass, K is the negative constant. Average life of an atom is this formula. Carbon 14. Anybody know what carbon 14 is about? Anybody? Anybody want to know?
Radioactive decay.
Yeah, I mean, I think carbon 12 is normal. I know this is math, and this is kind of nuclear physics. Most carbon is carbon 12, but a certain amount of carbon is this radioactive carbon 14, which doesn't mean it's dangerous. I mean, it's no more dangerous than walking outside and getting bombarded by particles coming from outer space. But when things are alive, they breathe in air and they absorb carbon 14 at a certain, it's in a certain ratio to carbon 12. And after you die, you stop breathing in this carbon, and the carbon 14 decays radioactively. So if you take a sample of something that's been dead for a while, you can compare these ratios and you can figure out about how old it is. So that's the reason they throw it into a math book. It's common. I mean, I guess it's not so much physicists are interested in it. For them, it's kind of a done, or nuclear chemists or nuclear physicists, it's a done deal. But if you're an archaeologist or,
Anthropologist?
I suppose, depends on what kind of anthropologist. I mean, some anthropologists are not interested in civilizations that are old. They're interested in existing, right? So, yeah. But anyway, okay. So the value of K is this very small number. Find the mean life. They tell you what the mean life is, right? It says m is equal to negative K. And they tell you K is negative 0.000121. And then the interval from 0 to infinity, t e to the negative 0.0001 t t. So I want to be smart alecky about it. There we go. That's the answer. Of course, if you like something better than that, since this is just a measurement, you could use your calculator. You could plug in this formula, and you can't say 0 to infinity, but you'll find if you put a big number like n, say 100, you don't have to put a million. That'll take the calculator a long time. I mean, e to the minus 0.0001. No, actually, what point is I mean, you're adding something, you're integrating something that looks like this. And I guess the question is, where is this so small that you don't have to pay any attention? I don't know. So let's do it the hard way. Right? So rather than futzing with that very small number, that very awkward number to write, we could just start off by saying, I know what t to the minus a t dt is, and what would we use to find this integral? I didn't hear you, but I did hear you.
Integration of parts?
Integration by parts. So we'll say let f equals t, g equals e to the minus a t, f prime equals 1, g prime, g equals e to the minus a t over minus a, means that this is now t e to the minus a t over minus a, minus integral here, e to the minus a t over minus a. And we're integrating this from 0 to infinity. So we really need a limit here, but I'm going to make believe you all can read between the lines. So if I plug in a very large t, this is a very negative number, e to a very negative number is goes to 0, right? So we have 0 minus, oh, we didn't integrate this yet. I guess I should do that first, shouldn't I? T over minus a minus now, same thing again, e to the minus a t, but now we're over a squared. Okay, so now this gets close to 0. Same thing here, right? Doesn't matter that it's over a squared. This one is negative, this is positive. So this goes to 0. Now we plug in 0 here. Oh, that's 0 again. Minus, oh, so we're going to get minus a minus. So what does this go to? This goes to e to the 0 over a squared, which is 1 over a squared. So our answer to this is negative 0.0000121 squared, so that goes away. And what are the units here? Oh, it doesn't have anything to do with m0, the initial mass. The average life of m, right? If you take a pound, its average life is such and such. Take half a pound, its average life is still such and such. They say what the units are?
Can I see the board again?
Oh, sorry.
Thank you.
And could you lower the blinds again?
Oh, absolutely. I just can't get away from those James Bond scenes where they always do that. And, you know, the floor and the sharks are in there. Okay, so square that number, and that's the mean life in what? Do they use units anywhere here?
No.
That's really sad. Because if it's years, well, still not very long. But if it's seconds, I think it must be like years,
Yeah.
because otherwise you would
Wouldn't
think
make sense.
there wouldn't be any left very quickly. Okay. So that's what that was about. Actually easy math, except complicated by the real world. Okay. Other questions on homework? No? All right, let me double check mine. So, no, comments on here? I'm gonna need this. Put it out here now. Okay. We're going to do a few things that I think are easy, because we've already done most of it. And then we're going to do something that's very hard. It's so hard that when I read the book, I was like, what? What are they talking about? I had to kind of carefully go over it and make it make sense to me. And then I was like, oh, that's very cool. I didn't know you could do that before this, but it makes sense. So we'll get there. The chapter title is, or the section title is Applications. And the first thing we're going to look at is area. Which we've really been, most of what we've been doing is with integrals that we think of as area. I think we've even looked at this particular idea before. You have two functions. And some limits here. And what you're interested in is, well, what's the area between these curves? Well, remember, even from basic geometry, if you have, say, an object like a square, and say there's an object inside of it, let's say it's quarter, and you want to say, well, what's the area of inside the square, but not inside the circle? It's really obvious. It's just the area of the square minus the area of the circle. Likewise, if you want the area between these curves, if you take the area below f of x, to the x-axis, and you subtract this area, the area under g of x, shorthand here, that's going to be the area. That's not a, we can call it a no-brainer, but it's pretty obvious. What happens now, though? Let's say we take this same situation, except now the x-axis is over here, and maybe one of them is above the axis, and one of them is below the axis. And now we want the area between here. And it's like, it's not as obvious, because we know we treat the area, below the axis. We can't. What's the area below g of x? I mean, it's not really. This is a negative area. So you could. Yes.
F of x plus the absolute value of g of x? Or
We're getting there. We're not quite at that point yet. We're going to get there. So one thing you can do is very strategic here. You just say, well, what if I just move these functions up? In other words, I say, let's see if I can draw this so it kind of looks the same. So now I have f of x plus some constant, some big enough constant to move it up. And I add, of course, I add the same constant to g. And now I ask the question. Well, clearly what we saw was correct, still correct. It's going to be this integral of f of x plus c minus this integral of g of x plus c. But, you know, this is just integral of f of x plus the integral of c minus the integral of g of x minus the integral of c. So we add this and we subtract it here, so we get rid of it. And we can see that this actually is this is no different from that. We don't have to do anything special just because it's below the line. So that takes care of that. That wasn't too hard. Now we look at a problem. Again, I think we've seen this, where f of x kind of does a loop like this, g of x does a loop like that. Now we have to be clear on what we want here, right? Do we want the difference in the area between what's under f of x and g of x? Because in that case, this piece here is going to count as negative area. Or are we really interested in the positive area between the curves here? And that's the problem, you know, I think is more interesting, the more likely you're going to run into. I mean, this could be some kind of fence, right? And this is concrete and this is grass, and you want to know what your area of your grass is. So now, what was it you were saying, Catherine?
Nothing.
I thought it was just like the, you know, kind of artistic direction, you know. And now,
Absolute value.
yeah, absolute value, right? So now what we really want is the integral of absolute value of f of x minus g of x. And in case it occurs to you, of course, this has got to be the same as this, right? It doesn't matter which one you do it. So if you really want the area between two graphs, it never hurts to put in some absolute value signs. Now, okay, that's great. We've got an expression, you know, to make it dx. But that doesn't really tell us how we're going to calculate it. But I think we've done this a couple times already, where we see you need to know what these spots are where the two cross, because that's the place where the sign of the area might switch. So we can treat this as integral from a to b of f of x minus g of x. Note f of x is above g of x here. And now we want to add that to the integral from a to b. Okay, so here it's switched. So here we want g of x minus f of x. Oh, not a to b. C, sorry. And then finally, you know, adding this last portion, which is c to d. Now f of x is greater again. So that's the easy part. I don't think it's going to be very hard to do these either. We're going to do some examples, just to get a feel for this. Make sure everyone is comfortable with this. So this first example says, what if we have y equals x squared and y equals 2x minus x squared, and we want to know the area between them? Well, picture is worth 1,000 words. So it might help to take a look at this, x squared, we know that one. I wonder what this looks like. Well, let's see, 0, 0 is a point on this curve. And it looks like 2, 2 is a point on this curve too. 2. It's over here. Does anyone remember what happens if you have a minus in front of the x squared?
Negative?
Yes, it goes upside down, right? So we have something like this. So we can see already the area we're looking for is just a little chunk in here. And we're going to want to integrate between 0 and whatever that number is. Well, how do we find that number?
Set them equal to each other?
Yeah. You know, they're both y's, so we say x squared equals 2x minus x squared. Or subtracting this from both sides, 0 equals 2x minus 2x squared. And divide out the 2. And then we can factor, and factoring it tells us that x is 0 or x is 1. So immediately we know we want to integrate from 0 to 1, absolute value of, again, it doesn't matter which one we pick, x squared minus 2x minus x squared. And I think that's pretty straightforward. I guess we'll complete it here. Let's put the absolute value outside, I guess. 2x squared minus 2x. X. Oh, it's going to start hiding, isn't it? Oh, unless I do this. So what do I get here? I get x cubed 2x squared 3 minus x squared from 0 to 1. 2/3 minus 1 equals 1/3. So that's the area of that piece there. Questions? I think this is pretty, as I said, I think this is pretty easy, straightforward stuff. All right, let's try one more easy one. Do I do these things too fast?
You erased it too fast.
Oh. Notice some students are like really technologically heavy, right? This problem is in the book, so you can look in the book.
Okay.
Sorry about that.
No, I'll just look at the book. Thanks.
Or on the video when you post it.
Yeah, you know, I'm going to. Ooh, somebody moved the.
Well, you were working on that board over there, so
Oh, you're going to be my AU guy. Okay.
Oh, okay.
All right. I'll just leave it to your discretion. Thank you. I appreciate it, because I know they come out crappy. have a budget for a full-time AV guy who can become the new Khan Academy, I guess. Okay, another example. Find the area between y equals e to the x and y equals x, but between intervals 0 and 1. Make it a little simpler. This one actually, it's really obvious that e to the x is always greater than x on this interval. Right? I mean, and the picture always is nice. Here's y equals x. And e to the x. Does it go underneath there? Huh. It certainly doesn't by 1, because it's, I don't think it does. I don't think it ever gets underneath there. Okay, so again, we just want this little area here. And the area then becomes, I don't need my absolute value because I know e to the x is greater, e to the x minus x. And again, that's a fairly straightforward integral, e to the x minus x squared over 2. 0 to 1, so it's e minus a half minus 1 minus 0. So that's just e minus 3 halves. I don't know if anyone else feels this way. When I just see an e, which is a number, right? 1.7 something. It looks kind of naked there. When it's got an x, it's like it could do stuff. But there it is. So 2.718 minus 1.5. That's my area. Right. Sometimes when you're doing these problems, the functions are not nice. They're nice functions, but they just try to integrate them. Trying to find out where they cross is not nice. May I erase this now? This is very old. So let's take a look at a problem like that that might lend itself to other means. Let's look at x over the square root of x squared plus 1. Y equals x to the 4th minus x. Well, it might not even be obvious what those look like, so let's use our resources here. So we've got x divided by square root of squared plus 1. Let's take a quick look at that. Problems. Let's see. Isn't technology good? Isn't it great? But when it doesn't work. Oh, sorry. Actually, in my defense, the 83 doesn't work the same way. Okay, let's see. Yes, there we go. And now we probably do want to zoom in. Okay, so that's our first equation, our first function. So let's plot the second one. That's x to the fourth minus x.
What's up with the X?
Sorry?
You put it up. The X
You
up.
did it again, huh?
Yeah.
Thank you. So we look at, we're going to take a look. So, there we go. So, again, we've got something doing this. And then we have something a little like a parabola going like this. Clearly we want to find this area here. So now we want to find out where they intersect. Well, it looks a lot like they intersect at 0. And of course, if you plug in 0, you can see this goes through 0, 0. And likewise, this goes through 0, 0. So that solves that. What about this? Well, you could kind of go down this road a ways. And you're going to have to square this. You have to square both sides. Oh dear, that's ugly, isn't it? You're going to get an x to the 8 minus 2x to the 5th plus x squared. And then multiply this. Now we're up to x to the 10th. Yeah, that's painful. But if you want an exact answer, that's what you have to do. And you have to look into how you would solve a 10th degree polynomial. Wait. But fortunately, since we don't need, at this point, we don't need an exact answer, technology comes to our rescue. Some of you may have seen this, but I'm not sure if everyone has. There's a nice little calc function called intersect for 5. And you have to give it a hint. Just doing this mechanically doesn't know which point you want. You could plug in a number, or you can just cursor over here. And you say, okay, there we go. It's my first curve. Now my second curve, yeah, it's over there. You see the little scar? So we say, yeah. Now it wants to guess. And if you come across something where it just sits here and rotates for a long, long time, maybe it's never going to get the answer, or maybe sometime in the year 3000, you might want to give it a guess. We don't have to. We're well within the bounds. Okay, so now down below you see it's approximately 1.18. You can use more numbers if you want. But, so we have 0, 0, and 1.818 something, and we don't really care what the y is. So now we have an integral from 0 to 1.118. Again, I'm going to put this in absolute value, although we can see that this is the guy. Well, this is the guy who's greater. To do that. X squared plus 1 minus x to the 4th minus x. Now, the book does this problem, and I think kind of absurdly, they go through and find the antiderivative of this, which is not, you know, it's not within your reach. It's not that hard, but it's a lot of work. And this is just a measurement. So why do that? Why go to that? Let's instead subtract. So let's first we plug in the integral we're trying to figure out here, and we can kind of graph that and make sure that it makes some kind of sense. Okay, so does everyone see that the area again is in this little bubble here? That's what we're looking for. And we can again use our calc function. We can say find the area. The lower limit is 0. The upper limit, we can just use 1.18. Actually, I found out if you don't want to do that, I guess you can be a little trickier. You can say answer, and it's going to do it right. Okay. So there you have it. You know, we just mechanically figured out the area to at least the accuracy we're interested in this case. All right. Okay. We have another type of problem which we're going to apply something we learned in the last section. I'm just bringing up my. I hope everybody. Hope not everybody. I hope everybody feels comfortable with the idea. If you want to do one of these numerical operations, you can go to my website and, at least for this class, use this. Use this. Is it okay to erase this now? No. Oh wait. Okay, so the idea here is we're going to use the Simpson rule here, and what we have here, we have a chart in the book which describes two vehicles and their speed. So there's time, there's velocity. And we have the velocity of the first car, velocity of the second car. They both start at the same place. It's important. And we have the difference. So again, we have some kind of thing going on here where we're going to start at 0 and I'm just going to put in a few of these numbers. And after 2 seconds, they're both moving. One's moving a little faster than the other. And the chart's in your book if you want to see the whole thing. But so we can integrate this using we can use Simpson's rule here. We're going from 0 to 16. seconds. And we have how many points? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, someone want to call those numbers out? 0, what's the next one?
13.
Just faster this way.
20. 20.
20.
23. 27. 28. 29. 29. 30.
Okay, and push a button. And Simpson goes to work. And it's 369, well, it's the units here. Miles per hour? No, that's not what it is. It's, distance traveled in the first 16 seconds. What's the distance? Is it feet or is it meters? Whatever. Okay, it's 369, whatever. This is like really boring calculation, obviously. I only really went for it because I think there's one interesting question. Remember, these are velocities, right? Velocity A, velocity B. What does this area represent? That's, I think, the only interesting question here. Give it thought. Give it some thought, you know. What are we doing here? We're integrating velocity. What do you get when you integrate velocity? You get distance. What is, you know, it's not the distance vehicle A went, it's not the distance vehicle B went.
What is the difference between the distances both traveled?
Displacement.
Does everybody see that? It's just how far apart they are, right? One of them went some distance, another went less distance. It's difference. So it's just how much space is between them. And if you like create a function where you know, some time t of our function, right? If you create a function out of it, this tells you over time what the distance between them is. And you can see that it's increasing. It's always increasing because the first vehicle is always going faster than the second vehicle. All these are positives, so you know, he's got like 29, 30 miles per hour faster, or feet per second faster than the other guy. He's going to just keep putting space between them. Right. Okay, one more in the easy category, except it's one of those where you can make it easy if you think about it a little. It's not actually that easy if you don't think about it. I guess the book wants to make a point in case it's not obvious to you. So what we want to do is we want to find the area between the curves described by x minus 1, fy equals x minus 1, and x squared equals 2x plus 6. So immediately, why is this different? Why is this different from all other problems we've looked at? There's something a little kooky about it.
The y squared.
Yes, but it's a little bit. You're on the right track. What does the y squared do to that equation there? Changes it. It's not a function, right? I mean, this is some kind of parabola going this way, and it fails the horizontal line test. What does it actually look like? Let's take a look. Y equals x minus 1, so that's y-intercept, right? It's a line like this. What does this go through? Y is 0. X is equal to -3. And if y is my brain isn't working today. I guess I shouldn't have turned this off, should I? Okay, let's wait while the system shuts down. Don't want to. Actually do some thinking here. So we have x equals y squared minus 6 over 2. So it's 0, it's, oh, okay. I'm going to go along, it's over here. It's kind of like this. Ah, there we go. Now, this is kind of hard. I mean, I want this whole area here. So how am I going to do that? Well, if I break it down, I could say, let's make this a function, right? In other words, it's two functions. Y equals the square root of 2x plus 6, and y equals minus the square root of 2x plus 6. So I guess that's this piece. I'm going to go from here to here on that piece, and then from here to here on this piece. And that's already, you know, it's hard. You do it, but it's hard. But instead, let's see if I can express this correctly. Looking at the problem, if we turn this way, it's not such a bad problem. How do we do that? Well, there's two ways to think of it. One is to think, instead of integrating along the x-axis, we're going to integrate along the y-axis. That's one way. The other is we could just change the x and y. And then it kind of flips for us. The area is not going to change. So let's try integrating along the y direction. I want to reverse these. So instead of y equals x minus 1, I get x equals y plus 1. And here I've got x equals y squared minus 6 over 2. So if I can figure out what these 2 points are, they're in the y direction. Now I'm integrating this way. All right, let's see if we can figure that out. Same way we always do, set them equal. Y plus 1 equals y squared over 2 minus 3. So 0 equals, let's say, 1/2 y squared minus y minus 4, or multiplying through y squared minus 2y plus 8 equals 0. Right? For those of you who are good at factoring, one's going to be minus, one's going to be plus. What did you use? Quadratic formula. It doesn't work out nice. Can't factor it. One of these is going to be plus, right? So 4 and 2 maybe? 1 minus 4.
Yeah.
That should be
Plus.
Good. Okay. So that means y equals minus 2 or y equals plus 4, that's exactly these points, right? Something minus 2 and something 4. And we don't need the x's, we can find them out if we want. Okay, so now we're golden. Minus 2 to 4. Again, absolute value. Looks like this is always going to be larger, so we'll save the. And that's it. I'm not going to do this one. I know you all can all do this. All right. Hope you found that easy. Let's try a few of these. Do not attempt number 4. Do attempt number 1, 2, and 3. And don't let number 1 scare you. Just be brave. Everyone who's seen number 1 is already going, oh, now I know what it means. Don't want to, well, you know, I know this, I would give you the advantage and privilege of being able to do twice, getting up on everyone else, and you would turn it down because you want to be fair to everyone else. Is that right? Okay. If number 1 turns you off, just skip to number 2 and 3 and come back. That's interesting. Daniel is not here.
Who are we going to get to do the problems on the board? Who are we going to get to do the problems on the board?
Well, since you pointed it out, you, right? I mean, no, I mean, the other thing, there's nothing interesting. Everybody's absent every once in a while. I just saw him earlier. Maybe he has something more important to do. I'm going to give you guys a minute or two, a few minutes. I'm going to excuse myself. I'll be right back.
Schoenbrun. Yeah, Schoenbrun.
I'm not sure if I would like find like the intersection points there. First one.
I realize it's 1:30.
2:30.
2:30. It's been an hour, so you can keep working, but when you're done, please take a break. Go out, get a little fresh air outside. It's really nice. But you know, be back in a few minutes. I guess I have to say, it's time flies when I'm having fun. Yes. Yes.
Is there a review sheet for the
I'll
midterm?
just do that. Oh, yeah.
Now, I will answer your question.
Oh, no,
I'm going to digress. You know,
I'll
you
bet
can
you
be
can too.
you can be a very knowledgeable, intelligent person. You know, not believe in ghosts or other nonsense or telepathy. But as a matter of fact, just before I left, I was sitting in the board and I was going, they've got a midterm on next Tuesday. I got to tell them about that. Oh, I should give them a review sheet. Yes. So, you know, it's like telepathy. No. It's not. Yes, I might have to make a note. I think that would be a good thing. Quite honestly, when you see the review sheet, you'll go, I didn't need this, duh. But it still will be helpful in that you won't be sitting there going, oh, but just write down all the things we did, and then you'll go, yeah, that's right. Usually when I do review sheets, rather than saying you should know this, I try and write in terms of, you should be able to do this, because that's kind of what we're learning here, to do something, to integrate, differentiate, solve word problems.
5 plus 2 is 7, minus 6 is 1, plus 3 is 4.
Oh, yeah.
Receive an email from Adobe with the attached invoice. With an attached invoice, do not click on the links. Okay.
guess I should be more specific when I hand these out. Is anybody trying to do number 3 by finding the antiderivative as opposed to using your calculator? Oh, I have so much admiration. You don't have to.
No,
You don't have to bloody your knuckles that way. But if you want to do it, go for it.
almost done.
You did it. Okay, all right. If I have an expectation on a quiz or a test, I will, do it this way or do it that way.
Okay, so in total that's plus 8. Minus 1. Oh, yeah.
So you having fun?
Yeah.
Didn't feel sad for a second. All right. Tell me if you want a few more minutes.
A few more minutes.
2 more minutes to beat your head against these. Anybody? You do one?
Yeah.
Okay,
I'll
good.
listen to this.
All right.
Plus one is.
Yeah, there you go. So that's All right. Is there any brave soul who wants to attack number 1 on the board? But why is number 1 different from any other problem? Anybody? I'm sorry?
Because it's
I mean, you know what?
I know, I just don't know
How do you say it? It's abstract, right? I don't tell you what n is, do I?
No.
Anybody? You want to try number 1? You have a question? Okay. Number 2. You have a question about number 2?
No, I was try number 2.
Oh, you want to do number 2? I reserve number 2 for you.
I have a question on number 1.
Yes.
So if you wanted to find where they intersect, then wouldn't you have to set x to the n equal to x to the n plus 1?
Maybe. So x to the n plus 1 minus x to the n 0. So x to the n plus x minus 1 equals 0. Yeah, that works. Yeah, you could do that. Does that tell you where it intersects?
0 and 1.
Great, we already know it's 1. Okay. Okay. Nobody wants to go and... It's funny because it's not really. See, this is really a perfect example of what I know. I always start every class, at the beginning of the year or beginning of the quarter with, be brave to do math. Sometimes if you're brave, you're rewarded by that bravery. I think some of you out there actually were brave and did it, but you're just not brave enough to come up here and do it. Well, we don't actually have to know, but it might help to know which of these is greater than the other. And between 0 and 1, x to the n is always going to be greater than x to the n plus 1. Everybody see why that is? I mean, if I divide through by x to the n, C1 is always greater than x, right? Because x, right, is always between 0 and 1. I guess at 1 it's 1. Okay, so this is just integral of x to the n times x to the n plus 1. We know how to do that. That's x to the n plus 1 or n plus 1 minus x to the n plus 2 or n plus 2, 0 to 1. X to the n plus 1 evaluated at 1 is just 1. This is also 1. And then the rest is 0, so we go. That's really all we have to do, but we could do a little more. Put it over a common denominator. N plus 1 times n plus 2. And what do I get? I get 1. This becomes 1 over n plus 1 over n plus 2. It wasn't hard, was it? You just gotta know how to do it. Because it's not a number. We deal with variables all the time. Actually, there's a. I made this problem up. I mean, the problem. The book had a simpler problem, but I was magnetically attracted to this problem, and I didn't know why until it came in. Take a look at this. This is like, this is y equals, actually, there's y equals x squared, cubed, right? See what it's kind of doing? It's getting there. And in analysis, you learn about something, like you guys learned about the limit of a sequence, maybe, or the limit, right? But you could have like a series of functions, like like y equals x squared, x cubed, and you actually could have a limit as n goes to infinity of f of n, and then what does that mean?
I have a question. How did you know that previously one of the intersections was 0? Because
Oh,
it wasn't equal to each other at 0.
I just said x to the n equals x to the n plus 1.
But 0 to the 1 is not equal to 0 to the...
0 to anything is 0.
Yeah.
Except for the 0 to the
variable
zeros.
types.
Oh, but the domain
So why-
starts from natural numbers.
Right.
Yeah, I'm sorry if I, n is a member of, which is sec 1. 0 is unnatural, or something like that. So anyway, when you study analysis, you find out this can mean different things. Like it could mean that, for all A members of some, domain, right, the limit of, as n approaches infinity of f of n of A approaches some limit. In other words, for every x, there's some, each of these has a point and it goes to that limit. That's one way. It's not the only way a function can have a limit. But the reason I was attracted to this is because there's kind of a curious thing that comes out of this when you look at the limit of this function. See, every one of these guys is continuous and differentiable. But what's the limit of these things? Right? It's just every one of these points is coming down to 0. And then there's a jump. So it turns out that you can have a limit of functions, every one of which is differentiable and continuous, and the limit is not differentiable or continuous. Actually, it's not continuous, it's not differentiable. Anyway, I don't know. You don't have to pay any attention to anything I just said. That's just something that comes up. And that problem kind of okay. All right, Flavie, you want to do number 2, right? Didn't forget, please. If you'd rather blue, let me know. Have a nice fresh blue in that box. Now, Flavie, you know, there's no shame in this, but when you get close to the board, everybody's intelligence gets cut in half. It's true. Take a close look at 5 minus 3 is, see? There's no shame in that. It just happens to me. I've actually developed a little immunity to it. Don't be embarrassed.
But that's still
It's unavoidable. It's another reason you have to be brave.
question. Pay no attention to me. This is you're doing great. So Flavi wrote a little. I think it's a triangle. Maybe it means delta or something. Anyone remember the English word we use to describe that expression? The difference? The b squared minus 4ac. Anyone remember what we call that?
Discriminate.
Who said that? Okay. Discriminant, yes. You see, racism is okay in math as long as you leave it to numbers. You discriminate between equations that give you one root, two roots, no real roots, meaning imaginary roots. Did I say something that's going to get me fired?
I thought you said discrimination was fine. I thought you were going to talk about some other thing. Not about nothing. Never mind. Just kidding.
It's discriminate. It discriminates, and it's okay. That's all I'm saying. I'm not talking about racial discrimination.
I thought you were talking about that.
Okay. What's the lower one on the board? Oh, minus one. Oh, minus one and two. Okay, so I think, see, it's the board doing it to you again. Thank you.
it up so people can, raise the board up so people can see. Yeah. I followed you until the last line, and then 6 plus 8 minus 3 is 5 minus a half. Well, I get the same thing. Thank you. Very good. You remind me that meticulousness in mathematics is a virtue. Two vocabulary words there. You know what meticulousness is? Very careful.
Oh, okay.
And virtue, you know, goodness. Everybody okay with this? Reminds me of shortcuts I've learned to take, which probably aren't good. But, you know, kind of going through this, finding the discriminant, and figuring out the points of intersection. Okay. Anybody have any questions about this one? Okay. Someone want to try number 3? Okay, you're on. Sorry? Go ahead, that's all right. You should, actually, let's, so you have more room, let's push this one down. And then you have 2 boards. Right on this one, and then, actually, if you start here, then just move it up. And just follow. Now, you should keep going. But I'm just going to point out to everyone there's an algebra moment in this that maybe everyone remembers.
Keep going, keep going. I want you to think about the question of why was he able to cross off that -1 there?
Because the instructions said first quadrant only.
Oh, yeah. So, it's hard work, isn't it? So what did you get?
I got 2/9.
Calculator just says it's 0.222222.
2/9.
So, obviously correct.
Yes. Everybody follow this? He figures out the points of intersection. I don't know why when I plugged into the calculator, I did that same mistake I keep doing, and it didn't show anything to the right, to the left of the axis, and I thought, oh, maybe could this be an extraneous route? It's not. It goes through there. But anyway, so we find this, the integral, and we work very hard, and we do substitution, and it all works out. But it's hard work.
Why were you saying -1 when the end there?
Because I made the same mistake on, I was foolishly trusting my technology here when I shouldn't have. And instead of plugging in 3x squared plus 1, I plugged in 3x2 plus 1. And when I graphed it, there was nothing on that side. And I thought, oh, I wonder if this is an extraneous root somehow. I wasn't paying attention. And I was wrong. It happens. Has it happened before in this class? I guess so. It'll happen again. Okay. Now I know I've been here for a long time. But this next part is the hard part. So if you want to if you want to get an A, you're going to have to pay really close attention. There's something here that looks like sleight of hand. It's not. First, let me ask, everyone here remember parametric equations? Just raise your hand if you don't remember parametric equations. Okay, all right. We'll do a very quick review what a parametric equation is. So, usually I describe a curve in terms, on a xy plane in terms of x's and y's. Like I could say, y equals x squared, or 2x minus y equals 5, or something like that. Or I could do something that you can't express as a function. I could say, like, x squared plus y squared equals 1. Does everyone know what x squared plus y squared equals 1 is?
Circle. Circle.
It's a circle.
With radius 1. With radius 1.
With radius 1, that's right. But this is not the only way to express this. I can express it in terms of a parameter. You want to think of it as, I guess, the theta parameter. And I could say x equals, did I get this right? Cosine theta, y equals sine theta. And there's no theta on this graph. Theta is just a parameter. And if you take theta from 0 to 2 pi, you get a circle. So a parametric equation is where you express x's and y's in terms of a third parameter. And sometimes you can go back and forth. Like if I said, well, let's square this, and let's square this. Oh, equals. And add the two sides, I get x squared plus y squared equals cosine squared plus sine squared is 1, right? So sometimes you can go back and forth. Sometimes you can't, or it's very difficult. So in those cases, sometimes the only way you can express a curve is parametrically. So what if I had some curve, and whatever it is, and I can't express it as a function. It might be a function. I can think of it this way, but I can't express it that way. I can only say y equals f of t, and x equals g of t. So is there some way to integrate under this? Turns out there is. And it's actually not something new. It's something we've done. But you have to watch carefully. So
So even though I can't express it that way, we can think of y as f of some function x, which I can't write, but my x I can plug in here. So this is f of g of t. So f of g of t is my y expressed in terms of t. So this is just my f of t. F of g of t is my f of t, and g of t is my x. Okay. Here's where you have to watch carefully. We have a rule called the substitution rule, and if I wanted to integrate over, this function, vary my parameter t from alpha to beta, we use Greek letters here, then I could write this. I could write the integral from alpha to beta of f of g of t times g prime of t dt. So it's integrating this in terms of my t parameter. Well, that's just the integral from g of alpha. That's an x, right? This is a t. This is an x. G of beta of f of x dx. Now I kind of did it backwards, but if you look carefully, this is exactly the substitution rule we learned. But being very careful here, keep in mind that f of g of t, that's my parametric equation for y, and g of t, which I use here twice, once directly and once as derivative, that's my parametric expression of x. Okay. So if I want to find this, but I only have parametric equations, I can evaluate this. Now that's a little abstract. So we're going to do a problem. And it's kind of a hard problem, but let's take a look at it. I first want to do a simplified version of it. So my x, which is, we're actually going to switch over from t's to thetas. My g of theta is theta minus sine theta. And my y, which is f of theta, is now 1 minus cosine theta. And I'm going to integrate this over 0 to 2 pi. And I want to show this, before I go any further, I want to do this with the calculator so you can kind of see what we're really dealing with here. So if you're not familiar with parametric equations, or even if you are, you might not be familiar with your calculator's ability to deal with parametric equations. So if you click on the mode button, you'll see 3-4 lines down. You'll see func, as in functions, par, as in parameter, parametric, pole, which is polar, and I don't know what seg is, but someday I'll learn.
I think that's a Q for sequence, maybe.
Oh, sequence.
What did I say?
Seg.
Seg. Oh, yeah. I think you're right. Sequence. And I still don't know what it is. Okay, but take a look here. We can say I want parametric. And then when you go to enter go to y equals, you'll see instead of just y equals, now you have x equals. So let's put this in here. So it's x is theta minus sine theta. So it likes t. So it's sine t. And my y is 1 minus cosine t. All right, and well, it's already set up to go from 0 to 2 pi. So we're going to do a graph. Let's zoom out of that a little. Okay, everybody see that curve there? It's called a cycloid. Where does that show up? Think if you take a wheel. Let's do it over here. If you take a wheel and you're rolling the wheel along, and you think if you could be wrong about this. You put like a magic marker here and let this roll along. I think you may get a cycle. And you can see in this particular example, well, actually, why don't we let me change this here. Let's change this to 6. -6. You can see that now we have 2 cycles. So 2 pi was the cycle for this. And just for the sake of argument, let's calculate. Oh, it doesn't know how to calculate the area under a parametric equation. So we can't do that. Not that way. Okay, so okay. Turns out this is not the problem I want to solve. This is a cycloid with radius 1. But the book wants me to do the same problem, but with some generic radius, of which these are the parametric equations. So the first thing I want to know is if these are the parametric equations. Oh, and this is over period from 0 to 2 pi r. First question is, okay, so let's think about this. So I have some function of the cycloid here, and I'm integrating it from g of, well, from 0 to 2 pi r, right? I'm drawing this wrong. I want the area under it, right? So f of x represents that function, which I cannot write in a nice, easy way. But this equation tells me that g of alpha equals 0, and g of beta equals 2 pi r. Well, where's my g? My g is r theta minus sine theta. So the question is, when is this 0? When is r times theta minus sine theta 0? Well, clearly if theta equals 0, 0 minus sine of 0, which is 0, is 0 times r is 0. So that's my lower bound on this second integral. Here I have 2 pi r equals r times sine minus theta, which tells me 2 pi equals theta minus sine theta. And then the question is, where is theta minus sine theta equal to 2 pi? Again, it should be rather obvious. Theta equal 2 pi. The sine of 2 pi is 0, so this is just theta equals 2 pi. Okay. We're halfway there. We want to plug in now f of g of t, which is big F of t, little f, right, of theta, right? It's just this, r times 1 minus cosine theta. And we want to plug in g prime of theta. Well, here's our g. What's g prime of this? I want to keep my r. What's the derivative of r theta minus sine theta in terms of, with respect to theta? Well, it's going to be r. The derivative of theta is 1. And the derivative of sine theta is cosine theta. So now we conveniently have an expression for the area under this curve that we can't express in terms of x, in terms of theta. Well, let's go ahead. Let's take out the r squared. 0, 2 pi. 1 minus cosine theta times 1 minus cosine theta is 1 minus 2 cosine theta plus cosine squared theta. Well, I'm rushing things, but you should remember that cosine squared theta, when we want to integrate it, what are we looking at? We want to look at cosine of 2 theta equals 2 cosine squared theta minus 1. So this just becomes cosine of 2 theta plus 1 over 2. Just going to look like this, theta. Okay. So it's sneaky here, and just call this 3/2. And we end up with r squared times 3/2 theta minus 2 sine theta plus sine 2 theta over 4, 0 to 2 pi. This was kind of tricky. The rest is easy. Whenever I plug in 2 pi and 0 into the sine, well, here it's the sine of 0 and 2 pi. Here's the sine of 0 and 4 pi. Those are just 0. So really, all I'm left with is this term, r squared 3/2 theta. I plug in 0, I get 0. Plug in 2 pi, I get 2 pi. So it just becomes 2 pi times 3/2 r squared. And the 2's cancel. So I end up with 3 pi r squared. Which, if you recall, when we had r equal 1, the answer was 3 pi. This is hard. This is really hard. you can do it. You just have to be very careful. You have to remember this expression exactly, and you have to look at what is f of x, right? F of x is f of, I'm sorry, you don't look at this. You can't find this. You have to look at f of g of t, which is f of t, and you have to look at, because you need it here, and you have to look at g prime of t, which you're going to be given. Okay. You have one more problem on your sheet. Please give it a shot. Parametric equation of x and y in terms of sine t and e to the t. And I tell you that on the interval, well, actually, I think it's the same. Yeah, I'm just. Yeah, you can assume the x interval here is from 0 to 1. So I'm giving you that explicitly. So give that a try. I'm going to give you a couple minutes. I'm going to be right back. do I erase this? I'm not going to erase the upper part. Just a reminder, this homework assignment on this section. I highly recommend you try and keep up right now because we are so close to the midterm. This, of course, is online, so you don't need to write it. 4, 7, 8, 9, 29. But it'd be good to come in Thursday if you have questions on any of this. They say try and keep up because right now this could be on the midterm and you want to be up to date on it.
To which section is the midterm going to be on? Like 6 points, everything from 11
From 0, I guess that's 5.1,
5.1 until 6.2.
to 6.2,
Oh, okay, wow.
which we will do some of Thursday. I haven't decided how much, but some of this next stuff is easy. If something is hard, I probably won't put it on this exam, just because I want to give you a chance. But,
You mean like this?
yeah, like this. But you have 2 days for this. This might be on there. Something like this. This is just fact. I just learned about this. They never taught me this when I was doing calculus. And parametric equations, which covers a whole bunch of things that you can't get a function for. You can't write out explicitly. It's very nice, I think. Okay. All right, so anybody want to do this one? We have a few minutes.
We need Daniel to come back.
Oh, don't count on Daniel. All right, let's take a look at this. How does this work? So we have x
x is equal to sine of t and y is equal to t.
Oh, thank you. My own, and I'm going to need g prime of t. Oh, isn't that special? And we don't have to worry about the limits because I told you right off the bat. Well, no, wait. We do have to worry about the limits. We do, okay. So this is from 0 to 1, with f of x dx. And 0 is equal to g of 0. I'm sorry. G of alpha equals 0. And G of beta equals 1. So that means G of alpha equals e to the alpha equals 0. That doesn't make sense. Anybody run into this problem? Couldn't help but speak up. X is oh, 2. X is g of t. Y is f of t. So this is sine of t, right? Well, t here is 0, right? This is sine of t equals 1. So this would be the arc sine of 1, right? So that's what. I'm not writing this down, right? Sine of alpha equals 0. So alpha equals 0. Sine of beta equals 1. So beta equals arc sine of 1. So this is the integral from 0 to arc sine of 1 of f of g of t, which is little f of t, e to the t, and derivative of this d prime of t, cosine of t, cosine of t, t, and this is just something you should, you can do this with a calculator pretty easily.
Wait, so how did you get just the e to the t there?
Okay. F of g of t, big F of g of t, is little f of t.
Oh, yeah.
See, this is f of x, right? And I plug in g of t here, right? F of g of t, right? That's my y, right? Y is, in terms of t, is little f of t, which I'm given.
Oh, okay.
See, it's tricky. You have to. So that's why this is little f of t. Okay, so anyway, this clearly is something, well, I guess you could go through it. I don't think we're going to get a fixed answer other than by the calculator. This is definitely a calculator problem. So I think anybody feel uncomfortable doing this themselves? Good. Okay, I think that's it for today. I'll be around for a few minutes. Yeah, questions still. I'm going to talk about something mathematical or otherwise. for the AV.
No problem.